Thanks, Luke. So, hello, everybody. I'm Paul. I work here in the Centre for Atmospheric Science, and I'm also employed by NCAS Climate as a sort of chemistry modeller. And I'm going to tell you today about heterogeneous chemistry, about the role of aerosols in influencing the evolution of the composition of the troposphere. And I'm going to do it from the perspective of someone who used to work in experimental aerosol science but is now a modeller, and also from the perspective of a user of UKCA. So I'm not one of the developers. I should acknowledge Luke and Olaf for putting the chemistry together, Graham Mann and all the people at Leeds for writing GLOMAP mode, and obviously Colin for doing so much work in coupling UKCA aerosol and UKCA chemistry together. So I can't take any of the credit for what I'm going to tell you about, but I hope to describe why you would be interested in aerosols from a chemical point of view, what their potential chemical impacts are, and then I've included at the back of the handout some slides about how you actually go about adding new chemical processes into UKCA. New aerosol chemical processes into UKCA. You're already experts in putting new chemistry in, but there's a little bit of extra stuff you need to do to think about aerosol chemistry in the context of UKCA. So if we break the atmospheric aerosol down into, let me just make sure it's the, if we break the atmospheric aerosol down into a kind of supermicron mode and a submicron mode, we can see that the composition of the aerosol, the gas and liquid and, the liquid and solid, sometimes a mixture of liquid and solid particles that we find, the composition is quite different. So in the sort of supermicron mode, we see on a global mean, kind of 50% or so of the aerosol is mineral dust, 40-odd% is sea salt, and then there are smaller components from things like volcanoes, industrial activity, that sort of thing. So this large mode, this coarse mode, is generated mostly by mechanical processes, the action of the wind on the sort of arid regions, lifting the mineral dust into the atmosphere, that sort of thing. The fine fraction is totally different in composition. We see a preponderance of things like sulfates and organics. There's an increasing fraction of nitrates, a certain amount of dust and so on. And the difference in composition basically reflects the different processes that generate the aerosol. So as I said, the coarse mode is mostly mechanically generated, wind blowing on the sea surface, that sort of thing. Whereas the fine fraction is, a lot of it is generated from gas to particle conversion. So we have pollutants emitted into the gas phase. They're oxidized. As they're oxidized, they become less volatile. They prefer to condense into the aerosol phase. So if we start off with something like NOx emissions, they're gradually oxidized to nitric acid. Nitric acid has a bunch of fates in the troposphere, but we might think one of the fates is to partition onto aerosol particles because of the low volatility, the low vapor pressure, and then it contributes to the aerosol nitrate. It goes into the condensed phase, and in the absence of evaporative processes, it stays there. So we see this nitrate just from the oxidation of NOx. And at the same time, we see SO2 being converted into sulfuric acid and then again condensing onto the aerosol, sometimes nucleating to give us this sulfate mode. And VOC emissions, again, they can be oxidized. Every time they're oxidized, their vapor pressure goes down by a couple of orders of magnitude, and so they tend to partition towards the aerosol. So you can see that the oxidation is basically creating these components of the fine fraction of the aerosol. The aerosol spans a bunch of, quite a wide range of sizes in the atmosphere, a few nanometers up to a few hundred microns. And the lifetime of the aerosol varies with size. So the coarse mode, the supermicron fraction, that experiences a relatively significant gravitational force and so is lost via sedimentation. The nucleation of new aerosol, which makes particles of a few nanometers, these nanometer-sized particles are lost relatively rapidly by coagulation. They have a high diffusion coefficient in the gas phase, they find each other, they stick together, they coagulate, and they generate larger particles by this coagulation process. So this is a fast loss by coagulation, this is a relatively fast loss by sedimentation, and in the middle there's a kind of size range where the loss processes are not as fast, and so the lifetime of this accumulation mode can be rather long. And you can see in the slide I've indicated the different ways in which the accumulation mode can be directly populated. So this accumulation mode, where the lifetime is relatively long, particle sizes, particle diameters of the order of 100 nanometers up to a couple of microns, the lifetime of these particles in the atmosphere can be significant. It can be days to weeks, and that's long enough for them to be transported around. So the aerosol is sort of being mixed around by the sort of advection of the atmosphere, and so you tend to find aerosols throughout the atmosphere. And because of this long lifetime, the integrated impact can be large. Apologies to the experts, by the way, for all this introductory stuff. So I think we're very lucky in UKCA because we've got GLOMAP mode coupled in. GLOMAP mode, I would say, is the state of the science sort of aerosol treatment in global models. GLOMAP mode prognoses a bunch of different components of the aerosol, so it treats sea salt, black carbon, organic matter. I still think dust is classic dust, isn't it, in 10.9?
Yes,
yep.
It is, but there's in UKSM1 it will be.
Yep.
It's still not mode of dust. It's still classic dust.
Yeah.
But there is development work going on mode of dust.
Yeah. So GLOMAP mode prognoses most of these. Dust is still treated by the old single moment scheme, but not only do we get the kind of the mass mixing ratio of these species from GLOMAP mode, we also get the number density, and that enables us to do some nice chemistry calculations. If you look using satellite products as to where the aerosol is, this is a plot of mass concentration derived from satellite products. You can see, sorry, this figure predates End the Rainbow, so apologies for the colour scheme. You can see regions of high aerosol loading in the Saharan regions, that's the Saharan dust. Again, over the Gulf, another dust-dominated aerosol distribution there. But you can see other sort of hotspots, Indo-Gangetic Plain, East Asia. There are lots of regions where the aerosol loading is high. And there are lots of different regions of the troposphere where we can find aerosols in large amounts. So not just in polluted near source conditions, but relatively clean maritime conditions can also be influenced by aerosol. Another slide that I cribbed off NASA. It's hopefully a movie. Yeah, of the different types of aerosols and how they sort of move around the atmosphere. So it's been broken up. This isn't in your notes, alas. No movies in the notes. We've got the aerosol broken up by the different categories. So you've got sea salt aerosol in blue. You can see, because the aerosol is generated by the action of the wind, higher wind speeds lead to larger amounts of aerosol loading. So in regions of really high wind speed, you get large amounts of sea salt aerosol. We've got soot from biomass burning regions. Amazonia shows up, sub-Saharan Africa shows up, Borneo, those kind of places. We've got dust again blowing over the Atlantic, Taklamakan and Gobi deserts, that kind of thing, Gulf states. And then we've got sulfate, which is our sort of secondary component from sulfur-rich fuel emissions, which is sort of more widely found in the Northern Hemisphere, reflecting the sort of distribution of the combustion sources. Yeah, I think that's it. Oh, and it's very nicely drawn the aerosol mixing, so you can see the dust and the sulfate mixing together. So what's the sort of chemical impact of these aerosols? We know that the pollution is degraded by the action of sunlight to form the aerosol. That's the kind of NOx to nitrate, SO2 to sulfate scheme. One of the primary reasons why people are interested in aerosol, of course, is because it changes the atmospheric radiation budget. So we have scattering effects to consider. But these scattering effects are also going to change the rate of photochemical degradation of pollutants. So that's going to change JO singlet D, for instance. That's going to change the OH in the region of the aerosols. And because the aerosols are affecting the photochemical degradation, then we've immediately introduced a feedback loop into our chemistry. If the photochemical degradation is modified, then that means that the rate of aerosol formation is affected. And so we have feedback loops in our models that may show up in our calculations. And this was demonstrated 2012, I think, by Drew Schindell's group, where they looked at the effects of NOx emissions on sulfate aerosol loading. So the NOx is a precursor to ozone, ozone is a precursor to OH, and OH is a precursor to sulfate aerosols via this OH plus SO2 reaction, one of the ways in which it can make sulfate aerosol anyway. And what they did was did an A minus B type of experiment that we love so much in these kind of modelling, in the modelling world, where they take NOx emissions at 1995 levels and then compare them with the effect of NOx emissions at 2030 levels. So the NOx emissions are going to change higher, they're going to increase, so the NOx emissions in 2030 will be higher. That leads to more ozone, and then that leads to more sulfate aerosol. And then that's sufficient to start to regionally modify the climate, this extra aerosol loading. More aerosol in this case meant a decrease in solar radiation, and that moderated climate change. So they're sort of saying the lucky people that live in India and round about, because their area is so polluted, they're actually going to not experience as significant a change in their temperature. And you'd have to ask them which they'd rather have, I suppose. The original and best sort of study of its kind, I think, is Frank Dentner and Paul Crutzen in 1993, where they basically took stratospheric aerosol chemistry and looked at its effect on the troposphere. So things like the removal of the NOx reservoir N2O5 onto aerosol particles, the loss of the HO2 radical onto mineral dust, direct uptake of ozone, those kind of processes. And what they did was just calculate zonal mean ozone as a function of time of year, and they are showing that in this plot, for instance, that in sort of northern mid-latitudes in the sort of winter months, there's a 30% reduction in ozone at the surface, 1,000 hectopascals anyway. And that's pretty sort of significant effect, and it's mostly driven by the loss of NOx reservoirs, which the NOx reservoir N2O5, which caused a decrease in ozone production. And N2O5 is favoured by conditions like today, low solar insolation, cold temperatures. So the effects were seasonal and regional. And I think that's the kind of effect that is still sort of unexplored in our treatment. And there's lots of chemistry that could be implemented in UKCA to kind of examine these impacts of aerosols on air quality, not just on the PM component of air quality, but on the gas phase component of air quality. So just to recap, the particulate matter in the atmosphere we know serves as a germ or the nucleus for cloud formation. We know it affects the solar radiation budget. In certain cases, it can absorb the outgoing radiation, so actually increase the strength of the greenhouse effect, sort of that kind of black carbon that can have a warming effect. But for the rest of the talk, I'm just going to talk about this idea that the aerosols are removing or transforming trace gases. But obviously that leads into more sort of current questions to do with what's the health effect of aerosols. So I'm just going to head off into a physical chemistry rabbit hole for the next sort of 10 minutes by telling you about what the chemical effects of particles in the atmosphere can be. And there's actually a few different pathways by which the aerosols might affect gas phase composition. The first is just simple partitioning into the aqueous phase. So if you have a soluble gas, it can be taken up into the aqueous aerosol or cloud particles. If you have a solid aerosol, you may lose gas phase molecules because they just stick onto the solid surface. Perhaps of most interest is the idea that gases can be reactively transformed. So the aerosol takes up a trace gas molecule, it transforms it by some chemical reaction happening within the particle, and then these transformed trace gases can then be released. And Ravi Shankara put it nicely in sort of 95 that the aerosols are interesting because they can take up these trace gases from the gas phase, and they enhance their concentration. You know, they're solubilizing them and they're concentrating them in one particle. And this enhanced concentration can open up new pathways. And that's something that the lab people are exploring as part of their research, but it's also one of the opportunities that we have to put in these new transformative pathways into a chemistry climate model like UKCA, like UKCA. So our overarching chemical equation is that we're going to say that the species X is lost from the gas phase in a first order process. So the species X collides with the aerosol. The rate of collision is obviously going to be proportional to its concentration in the gas phase. But if we isolate the concentration and just look at the other stuff, the rate of collision is going to be it's going to depend on how much surface area the aerosol presents to the gas phase, and also the speed with which the gas phase molecules move around. And you can calculate that trivially. The mean molecular speed is 8 kT over pi m. So this surface area density, units of meters squared per meter cubed of gas, and the mean molecular speed control part of our uptake process. But the final step is this parameter gamma. And gamma is our reactive uptake coefficient, and it's a probability. It's a probability that on collision with the aerosol surface, X is lost, and so it ranges between 0 and unity. And this is where most of the physical chemistry resides. So to a first approximation, you can work out the impact of your aerosol on your gas phase composition by estimating or retrieving from the model the surface area density, calculating the mean molecular speed, and then having a think about what gamma might be. But obviously by taking gamma equals 1, you can always work out the upper limit of your process. Let's just say we were having a strong cup of tea on a Monday morning and thinking about whether or not you want to implement a new process in UKCA. Well, the first thing you want to think about is, what's my surface area density? And you can pull these out of Seinfeld and Pandis, as I have done with my smartphone camera. Apologies to them if they're watching on the video link. But what you see in Seinfeld and Pandis are plots of number density, surface area density, and volume density for typical aerosol or atmospheric conditions, so rural, continental, free troposphere. And you can see this one here is the surface area density. You can see that the maximum of the surface area density is in the accumulation mode, and you can also read off values in very helpful units of micrometer squared per centimeter cubed, and plug that into your calculations. And if you want to get an idea of how the aerosol varies with altitude, that's also in Seinfeld and Pandis, page 375. You can see that some aerosols are decay as you get away from the surface, and some are relatively well mixed. So again, just have a think about where the aerosol is when you're doing your back of the envelope calculation. Okay, back to our master equation. We've got a back of the envelope way of calculating all of these things. The uptake coefficient contains the physical chemistry that you might need to think about. And why would you need to think about it? Well, in general, experimentalists report gamma at 298 Kelvin and 50% RH. So you might have to think about how gamma might vary with different temperatures in the atmosphere and different conditions. So that's where the physical chemistry is, and there are extra bits in the handout that tell you how to estimate gamma based on physical chemistry theories. It is tempting just to take the number from the paper and put it into the model, but I think there is scope, given the complexity of the treatment that's available in UKCA using mode aerosol scheme, to add some value. And you can ingest the temperature and the relative humidity of your box to treat that kind of dependence on atmospheric conditions. It's worth saying that the resistor framework provides the best way to think about how gamma might vary, but there are other modelling frameworks available. And this resistor framework is basically trying to describe the loss of the species X from the gas phase into the aerosol phase as a collection of coupled processes. So first of all, my species X has to find the aerosol surface, then it has to transfer across, and then it has to do something in the aerosol phase. And the resistor model, originated by Peter Dankwerts and sort of developed further by the Aerodyne people, expresses these coupled processes as a kind of electrical circuit. So, you know, I've got my overall flow of molecules from X in the gas phase into the condensed phase, and I'm saying that each one of these processes might function as a bottleneck. So there may be some rate determining process in each one of these. So, you know, it may be hard for the molecules to find the surface, it may be hard to transfer across, and so on and so on. So following the electrical circuit analogy, I'm saying that my overall rate of transfer is basically a kind of sum of resistances. Some are in series and some are in parallel, so a kind of Kirchhoff's law type of description. And the value of gamma can be set by any one of these processes. So if any one of these is incredibly small, then that dominates the overall value of gamma that I retrieve when I reciprocate this sum. It says there. And if there's no reaction, if there's no gamma reaction term, the resistor model says that you basically expect the aerosol to become saturated in the trace gas of interest, and that means that over time there'll be no net uptake. So the rate of evaporation will match the rate of adsorption. But if you have some loss, some extra sink in your aerosol for your species of interest, then the uptake will proceed constantly over time. So I'm just going to skip over these because they're only there for reference. You can estimate gamma G, the resistance due to diffusion, using this formula. That gives you a quantitative estimate of that term. And gamma G becomes small when the particle gets large or when the diffusion coefficient gets small. We can go on. The solubility term basically depends on the Henry's law solubility of our trace gas of interest and the diffusion in the aerosol droplet, so the rate at which the trace gas gets away from the surface. And if you just want to estimate how much of your soluble species what fraction of your soluble species goes into the aerosol, you can estimate it quite simply using the Henry's law coefficient and the volume mixing ratio of the liquid water in the atmosphere. Gets worse, right? We can go on and write something for gamma reaction. It depends on solubility, temperature, diffusion in the aerosol phase, and reaction. And it also depends on particle size. So there's a bunch of terms in there. I hope I've defined them. But if not, they're all in Finlayson Pitts and Pitts. That would be my reference. And yes, there's one more for solid surfaces. Just a relatively simple expression that depends on the equilibrium constant for partitioning between the gas and the solid phase. Okay, so they're just there for your reference if you ever want to go into detail. But basically you can do a back of the envelope calculation once you've got the surface area density and a value for gamma. You can then calculate the first order rate of loss of the species X from the gas phase, and you can compare it with other relevant rates. An example might be reaction with ozone, the dry deposition rate, wet removal, so on. So, you know, does my rate of loss into the aerosol compare favourably with these other processes? If so, then I probably better put it in. And I also advocate box modelling. There are box model schemes available for download. You can get the KPP scheme from Adrian Sandu's site. Rolf Sander has made available, if you ask him nicely, the Mecca model, which is extremely pleasant to work with. And then Baron Henderson has put on GitHub this DSMAC model, which uses KPP and puts some wrappers around it to treat aerosol chemistry. So there's lots of more quantitative ways moving on from the back of the envelope to assess your aerosol process in context. We can also just put it straight into UKCA if your conclusions justify it. There is a section in the tutorial about how to work with heterogeneous processes. Basically, you're just defining a new reaction. So in this case, I've got chlorine nitrate plus HCl is making 2 Cl atoms and nitric acid. This is classic polar stratospheric cloud. chemistry, which is responsible for ozone depletion in the Antarctic spring. And you'll see that it goes with the stratosphere and strat-trop schemes by this identifier, and I just add it in and then I do some extra work. But first of all, I think about what is the reactive transformation that's going on. So in this case, my ClONO2 and my HCl are meeting in the aerosol medium and releasing these three species. There's also some aqueous phase chemistry. So in this case, we've got SO2 and hydrogen peroxide reacting together, not being released, so they are lost from the gas phase, and this appears in a whole bunch of the different chemical schemes that are available in UKCA. So your first step is to add in a reaction of interest, and then you have to do a bit more work. You add it into, I believe, I'm still finding my way with 10.9, you add it into UKCA Chem Master in the RAT HT1 array, and make sure you include the identifier for the scheme of interest. So here's chlorine nitrate plus water, that's in strat and strat-trop. Here's N2O5 making nitric acid, that's in trop-het. You just need to make sure you put it in the right scheme. For the stratospheric aerosol, the treatment is slightly different. You have to modify UKCA hetero mod. It's worth saying that the number of heterogeneous reactions is hard-coded here, so you need to make sure you increase the size of HK. And then you look for the calc-K PSC subroutine, which calculates the rate of PSC reactions. And when you find that, you'll see that each first order rate coefficient is calculated in this kind of way. This is K PSC number 2, and it's calculated as C, that's that bit there, times the surface area, that's that bit there, times gamma. So the formula that I described at the start is what's used for the stratospheric chemistry, and then there's always a magic fudge factor of 100. Those rates that are returned are then divided by the concentration of HCl, because the rates are expressed in a bimolecular way elsewhere in the scheme, and then they're passed back into the RK array, which contains the rates which are then passed into ASAD. The mode aerosol is also slightly different. There are the call graph for the 10.4 version of UKCA is sort of excerpted here. You can see that their UKCA main makes a call to UKCA aerosol CTL. UKCA aerosol CTL makes a call to UKCA trop-het chem, and then that goes on to calculate the het chem rates over here. So there's a sort of hierarchy of calls through the UKCA call tree to calculate these rates, which you're then going to pass back into ASAD. So passing the, sorry, I skipped on a few slides there. Passing these heterogeneous rates into ASAD is a little bit complicated. First, we define our reaction of interest. So this is, there are two currently defined in the UKCA Chem Master. There's N2O5 makes nitric acid, the kind of Dentner and Crutzen process, and then there's HO2 makes half a molecule of hydrogen peroxide. So there's plenty of scope to add extra reactions there, I would say. The thing to remember is that ASAD takes as inputs these 1D arrays, these Z columnar vector type things. So a lot of 3D arrays are reshaped into 1D arrays before they're passed into ASAD. So this is pressure in a kind of Z columnar vector form. This is temperature reshaped into the same form. There's quite a lot of that going on before you pass arrays into ASAD, because that's what ASAD expects. So here's our heterogeneous rate, RC het. The heterogeneous rates are stored in the all NTP structure, I suppose you might call it, and certainly it contains within it arrays. So we're getting our heterogeneous rates out of this NTP array, and we're reshaping it for use in ASAD. There's a call to ASAD hetero. It takes as inputs the RC hets that we just created. And what it's doing in ASAD hetero is it's assigning these rates that we pass in to the right bit of the RK array. So there's a kind of find reaction call, and then we're we're filling the RK array that ASAD needs to calculate the new tracer values from this RC het array that we pass in. So almost everything that you do with aerosol chemistry in UKCA is designed so as to pass into ASAD some new rate that it's going to use in the calculation of the updated tracers, the stuff that Oliver Wilde talked to you about earlier in the course. Okay, and so once you've filled RK from RC het, ASAD does the rest and updates the tracers for you, and then control is passed back to UKCA main. But where do these rates come from, which I haven't said yet? Where does this RC het or this all NTP array, how does that get filled? Well, it gets a bit hairy, but what's happening here is that we are calling UKCA trop hetchem with an input parameter, or an in-out I think it is, which is het rates. So maybe it's just an out. We're going to fill het rates using the UKCA trop hetchem subroutine. And then once these het rates have been returned, they have to be inserted into the NTP array. So there's an insert segment call with this array being filled with these values. That should all be done for you, but you'll see that there's one for each species. So if you add in a new het rate, you're going to have to add in, and you're going to have to expand the NTP array, and then you're going to have to fill it.
This is being done because the UKCA mode is being called after the chemistry.
Exactly what I was going to say, but you can say it for me. There's a kind of operator splitting going on in UKCA where the call to the mode scheme is after the, well, you know, it's after the call to the chemistry scheme, isn't it? So basically what you're using is the heterogeneous rates from the previous time step. And because we are not expecting the aerosol field to vary very much on the sort of 20-minute chemical time step scale, I think that's a reasonable approximation. But the thing to remember is that you've got to expand the size of the NTP array to store any additional rates, and then you've got to live with the fact that there's operator splitting going on. So you can see there's extra stuff that needs to go in trop hetchem. Okay, that's the end of my show. I would say that I think the way that UKCA combines chemistry and the GLOMAP mode scheme gives us tremendous power, and a lot of new chemistry is available for study. The new tropospheric heterogeneous chemistry routines are very powerful. You can define uptake. If you look inside the trop hetchem routine, you can define uptake onto different aerosol modes as a function of temperature and other parameters of interest. And it's a massive improvement over the version 7.3 treatment, which was a sort of single moment scheme without things like a prognostic sea salt scheme. So we're really, I think, standing now in an exciting place, and it's not to say that you shouldn't use the box models to build up your understanding, but once you're ready, UKCA mode offers quite a lot of new and interesting sort of opportunities to do some new studies. Okay, thanks very much.